Much for joining today. Yesterday, maybe I should apologize for yesterday. I was not able to join because we had a huge power failure and my Wi-Fi, everything was not working, so I could not join. So we continue today from where we left off the day before yesterday, where I had started to talk about data preprocessing. Okay, let me remind you the entire scheme of things that we are doing so far. We started with understanding why data analytics is important, what is the scope, and what all we can do with data analytics. We followed by saying that we can we need to explore a language that can help us to do data analytics. We said the language of our choice was Python. We did basics of Python, which included we used basics of Python. We use which included operators, functions, modules, uh, data types, and so on. Once we did basics of Python, we started with the different packages or the famous packages within Python, which were NumPy, Pandas, Matplotlib, Seaborn. There is one more package that we look into, scikit-learn, which will come when we reach machine learning. With that, we said, let us move to the next step, which is data preprocessing, which we said is one of the basic steps that we need to do before we can enter into training our models. Okay. And what we discussed in the last class was why we preprocess data, to which we answered that we preprocess data because it is dirty. And when we say dirty, we mean that it is either incomplete or noisy or inconsistent. Okay. And we saw examples of what does it mean for the data to be incomplete, what does it mean to be noisy and inconsistent as well. We further saw that 80% of the time and budget most data scientists will spend on in most data science projects, we will spend 80% of our time in collection, cleaning, and preparation, which is a huge chunk. So we need to be, of course, we need to be familiar with what are the steps and how it can be done. Okay. The major tasks in data preprocessing are data cleaning, data integration, data transformation, data reduction, and data discretization. Okay. We also saw that data cleaning has further filling of missing values, dealing with noisy data, correcting inconsistent data, and removing redundancy caused by data integration. And we saw to fill missing values, we could do multiple things. One is just ignore the data. We saw that this is not a very good method as we will have loss of information. Other option is to fill the data manually, which again we saw is either tedious or infeasible. And finally, we saw that we can fill it automatically. And when we say we want to fill it automatically, we can do again multiple things there. We can either create a new global constant, like an unknown class or a new class, or we can populate with the mean, median, or mode. Or we could use an educated guess or using heuristics from other parts of the data. So to fill this missing value, if this if all the three maybe data helps us find out what could be this missing value, we could use that information to fill. To deal with noise, we saw a method called as binning, which helps us to take the variation out of the noise and brings it to uh, brings us some kind of stability. We saw that we can do that by dividing the data into multiple bins, and for each bin, either we smooth the bins by binning by taking the values to the bin boundaries, or we smooth the bin by replacing by mean and so on. We also saw how to handle outliers. We first discussed what are outliers and what is the difference between outliers and noise. We saw two methods. One is called as clustering, one is called as curve fitting, that helps us to take the outliers and bound it into either a box, or it can take the outlier and reduce the value or increase the value depending upon the case to the nominal value, which can be represented either using clusters or curve fitting. We talked about data integration, which is when we combine data from multiple sources. Then what happens and how do we do things? So we looked at we saw that okay, we had done the same for the movie lens dataset, where we merged the ratings data frame with the movies data frame. Okay, we also saw data transformation, which is basically normalization and standardization, at least in our context. And we saw there are two ways of doing that. One is the min-max normalization, which converts any range of data in the range in the range of new max and new min. Generally, we keep it to 0 to 1. That is one option. We also saw Z-score normalization, which takes any data and transforms it to 0 mean and 1 standard deviation. Okay. And both of these are very helpful so that we don't give our machine learning algorithms bias because of the range of the features. Okay, so if we keep all of them in the same range, then the machine learning algorithm will not give additional priority to some of the features. Okay, and that is where we had stopped in last class. Okay, let me continue ahead and talk about a few more things in data preprocessing. I think then we will quickly move on to looking at an example of how we can do these things hands-on. Okay, so data reduction. So this is again a step that we do sometimes. It is not always used. It depends upon a case-to-case basis. And the primary reason for doing data reduction is when we find that the data is too big to work with. Okay, we have too big data. So as a thumb rule, generally in data science, more the data, the better. Okay, generally we want more data. The problem is if we have more of irrelevant data, then we get into trouble. So when we say more of irrelevant data, what does that mean? Okay, so many times you will find that let's say within our data science problems, when we go ahead, we talk about machine learning. One major set of problems that we try to solve is classification problems. Okay, classification problems are where the machine will try to classify the data points into different buckets or into different groups. Now, if these groups don't have equal representation, that is, let's say I'm trying to classify images into cats and dogs, and I have a total of 1000 images. Of those 1000 images, I have 900 images of cats and 100 images of dogs. Now, this is a this is a case of imbalance because my data is prejudiced or biased towards being of a cat rather than of a dog. And if I want my model to work well, I need to have some sense where I have equal or similar number of data samples. So I have then two options. I have to either reduce the number of cats or I have to either increase the number of dogs. Better is to increase the number of dogs by going out and collecting data. But if that is not a feasible option, then sometimes I would want to reduce the number of cats that I have. In this case, this is a very bad example because for a machine learning problem like image classification, 1000 images is nothing. If I have, let's say, let me scale this example to I have 1 million images, okay, of which I have uh, 1 million is 1 million is 100K. Yeah, 1000K. Okay. So out of those 1000K, if I have 900,000 of cats and 100,000 of dogs, then this is a trouble. Then in that case, I would reduce that 900,000 to somewhere around 100,000. One way to do that is reduce the data. Okay, so that is one cases where we want to reduce the data when we have too many instances of a particular class which we don't want. Okay. Other reason could be when you want to reduce data when there are too many features. Okay, so the too many features means there are too many columns of data. We saw within the movie lens data that we had 3 or 4 columns, right? Movie ID, the name of the movie and the year, and the genres. So just 3 columns or 4 columns. Okay. Now sometimes we have as many as maybe 200 columns. That is too much data. That is too many dimensions of data. In that case also we would want to reduce the number of features or reduce the number of attributes so that we can have a reduced set. Now the thing is, when we are doing this reduction, what we don't want to do, okay, what we want to do here. So when we reduce this data, we are trying to obtain a reduced representation of the data set that is much smaller in volume, but yet produces the same or almost the same analytical results. Okay. So basically, we don't want to lose the information from the data, but we want a smaller data. Okay. We don't want to lose the information from the data, but we want a smaller data. What we mean to say is, from a smaller data set also, we want to have the same analytical results as the bigger data set. Now, this is very easy to say, but it's very difficult to do, because if you reduce the size of something, you are bound to lose some information as well. Okay. Now, what we are willing to lose is, we are willing to lose the information that is not useful, thereby not affecting us. Plus, at the same time, we are not willing to lose information that may be useful for us. Those are generally analytical information. And this is something that is very probably advanced. Interestingly, in my years of experience, I have never come across a case where data is much for me. Okay, but I know of people where we have too much data and then we have to reduce, and there are different strategies for doing that. Okay, for dimensionality reduction, we have strategies like dimensionality reduction, aggregation and clustering, sampling, and so on. Okay, so let me show you an example, a few examples of dimensionality reduction. Within dimensionality reduction, what we're basically saying is, I have too many features. Let's say I have 200 features, which are too much for my machine learning algorithm to handle, and I want to reduce the number of features to 10 features. Okay, so out of 200, I am just interested to get 10 features. The question is, how will we do the selection? How will we choose some feature is more important than some other features? There are different ways of doing that. We have direct methods where we try to see if a minimum set of attributes is sufficient for a task. That is, why we have so many data points and what is the purpose of this data. When we're using it for a machine learning algorithm, the purpose is to train the model. Okay? So when we are training the model, we want to see what is my requirement, what is the level of accuracy that my problem statement requires. And then for that level of accuracy, I will slowly, maybe I will start with just one feature and see what accuracy I get. And then I will start increasing the number of features. So let's say with one feature, I have 50% accuracy. With two features, I have 80% accuracy. With three features, I have 90, and maybe by 6 or 7 features, I have 95% accuracy. And the way that we started the problem, we said that 95% accuracy would be fine. In that case, I will stop. Even though I have 200 features, I will not incorporate all of those features within my model. I will limit my discussion to either 6 or 7 features. Okay. So that is one way of deciding direct methods. Other way is, we can also talk to the domain expert. So let's say you're trying to work in the finance, in the housing industry, real estate industry. You're trying to deliver a solution, but you don't have much experience in real estate. In that case, you can take help of a real estate practitioner who is working in the field for maybe 10, 15, 20 years, who will easily be able to tell you what are the features that are important for your model. And we can take that help, and then we can choose the number of features or choose what features should be used. So these are direct methods of doing dimensionality reduction. Then there are indirect methods of doing dimensionality reduction that like PCA, Principal Component Analysis. Okay. What PCA does is, it tries to find out a reduced representation of all of my data. So it will take that 200 columns, and if you tell it that, okay, change these 200 columns to, change these 200 columns to, let's say, 5 columns. It can do that. What it will do is, it will combine these 200 columns in such a way that the variation of all the 200 columns are mapped into this reduced model of 5 rows, 5 columns, or 6 columns, or 10 columns, depending upon the case. The trouble with this method is, once you combine these features, then you don't have individual features. Okay. Then let's say if I have features for a house prediction algorithm, I have features like the number of square feet in the house, uh, the number of rooms in a house, does the house have a garage or not. So when I take these things, these features are very meaningful. These features make sense to humans. As we read, we can understand, okay, what do they mean by square feet area? What do they mean by number of rooms? But when you combine them together, then we come up with new features. Okay, and these new features have no relation to physical quantities. So they are just numbers, and it is difficult to relate those to what is happening. So let's say if you join these three numbers, the square feet, the number of rooms, and if there is a garage or not, you end up with some number, and that number, this one number has a representation of all these three quantities. So it becomes very difficult for us to understand why our machine learning model may work. And that would be one of the reasons that PCA would not be used. So again, depending upon case to case, if we are really stuck with the case of dimensionality induction and we don't have a way of reducing a number of features without losing data, then it makes sense to use algorithms like PCA, okay, SVD, ICA, all three work in the same direction, uh, where they are trying to reduce the number of dimensions by combining the multiple features together and coming with a combined form. Okay. Then we have methods of data discretization. So data discretization is basically uh, taking a range of multiple attributes and dividing it or replacing it by some common value. Okay. So again, when we are trying to do discretization, we should probably first understand what are the different type of attributes that we can have. Okay. So we can have three kinds of features. We can have nominal values, which are values from an unordered set. We can have ordinal values, which come from an ordered set, and we can have continuous, which comes from real numbers. Let me give you examples of nominal and ordinal. Let's say if I'm selling equipment or home equipment in my shop, and uh, I have gadgets like a vacuum cleaner. So let's say I have in my data, I have a column called as equipment. Okay, let me write it neatly. I have a column called as equipment, for which I have data like a vacuum cleaner, a television, a mixer, and so on. Okay. A mixer and so on. Let's say I have these three equipment, 1, 2, and 3. And let's say I have another column called as class or quality, to which I have values like high, medium, and low. Okay. So both of these cases, and let me add, maybe let's say, let me add one more feature like price. Okay. So let's say a vacuum cleaner costs maybe 8,000, a television costs maybe 20,000, and a mixture costs, let's say, around 3,000. Okay. So let's say I have such data. I see that all three columns, equipment, quality, and price, these are different examples of these cases. Okay. Maybe let me ask you the question of these three types. Okay. Nominal, ordinal, and continuous, which are, let me call them A, B, and C. Can you tell me equipment column is which kind of attribute? Is it of type A, type B, or type C? What do you think for equipment? What kind of attribute is it? A, B, or C? Okay, many people are saying A. Very good. What type of example do you think is quality? Okay, excellent. And the third case, price? Okay, excellent. So let me also give you the reasoning. So when you say nominal, we are looking at values from an unordered set. So if I tell you to put them in order, vacuum cleaner, television, and mixer, what should be order 1, 2, and 3, then it is very difficult to do that. Basically, we cannot do this. Why? Because these are three different categories of stuff which are nominal in nature. That means you cannot assign a priority. You cannot assign a ranking to vacuum cleaner, television, or mixer. Okay. But if you look at the feature quality, we have three words, again categorical, low, medium, and high, but we can assign some level of order to them. Okay, we can say that okay, medium is better than low, and high is better than medium. Okay, if you have to put in ascending, you'd put low, medium, high. To put in descending, if you want to put in descending, you would put high, medium, and low, and so on. And then we see our third category, which is continuous numbers. So now we know here that these are not categories. Okay, in fact, I could have kept things like 8,900 and so on, right? So these are, this is continuous numbers which can take any value depending upon the case that we're looking for. Okay. So these are the three different type of features that we generally encounter within any data science problem. We also have one more, which is Boolean. Okay, that is either a value of 0 or a value of 1, saying that the whether there is a quantity as true or false. Okay. Now, depending upon this, depending upon the kind of data, you will have different discretization methods. Okay, now discretization is basically dividing range of attributes into intervals and replaced by common value. Okay, which is exactly what we saw we did in binning, right? In binning also we partitioned the data into multiple groups, and for each partition we replaced by certain things, or we transformed certain things. Either we could take it to the bin boundaries, or we could take it and replace by mean or median and so on. And those are ways of discretization of numerical data. Okay. Now, when we have concept hierarchies, or we can do something called as concept hierarchies. Okay. So for data discretization, what is concept hierarchies? Is when we convert low-level concepts to high-level concepts. Okay. So an example of that is, let's say I have age as a number. Okay. So I'm collecting data, and I have age which varies from maybe 5-month babies to 60-year-old seniors. Okay. In that case, what I could do is I could divide my age into multiple groups. Okay, those groups can be a child, youth, adult, senior, and so on. Okay, so what I'm doing is I'm converting a low-level concept such as age in numbers to a high-level concept such as children, to groups of people. Okay, similarly here also, when we look at the price data, I could take price and divide it into price could be a low-level data, which we divide into high level data like cheap, costly, or very costly, or we can say less than 5,000, between 5 to 10, 10 and greater. Okay, so these are different groups that we could divide our data into, and that is what we mean by data discretization. That is, we have numerical data, or we have something like this. We try to convert them into an ordinal, or we try to convert them into a continuous group of data. Sorry, not continuous, nominal or unordered set of data. Now, in summary, this is a big issue, right? Data preparation or data pre-processing is a big issue. Why? Because we spend most of our time within this problem. Okay, you will see very very quickly as we come to data science problems that we will use 80% or even sometimes more time of our data within the data pre-processing parts. Okay, we saw that the major tasks are cleaning, integration, reduction, feature selection, discretization, etc. So those are the things that we'll do. Okay, and generally we need to get adept at using pandas and maybe even NumPy to be able to do many of these tasks. Okay, now many proposed methods, but it's still an active area of research. Okay, so there are many researchers who are working within the data pre-processing. Many people are trying to automate data pre-processing in some way or the other, where we or either automate or semi-automate this, so that our algorithm will itself tell us what is to be done, how it is to be done, and we have to either sit and approve it or reject it. Or we are also moving towards automatic working on these ideas. We're also moving in new means and methods and tools where we can use to pre-process our data. Now, further data pre-processing basically is very subjective topic. Okay, there are different people who will take different approaches, and it's very difficult for someone to justify why they have taken something and what was the reasoning behind it. It's all about what a person thinks about the data and how they want to divide, partition, uh, play around, fill with missing values, and so on. There are so many decisions we have to take, and these decisions are not always backed with proper results. Many of the time, it is the experience of the data scientists, the insights they have gained from the experience from working on other projects, and so on. So, thus I say that it all depends upon data. It is an art, not a science. So, with this, we have finished the theory behind data preprocessing. Let me share my laptop screen so that we can go towards a problem and then try some of these methods on that data set so we can see how things work out. Okay, let me stop broadcasting. Okay, I hope you can see my laptop screen as well. Uh, this problem that we're looking at is a very famous problem that that we come across, especially when we are doing uh, when as beginners we are looking at data science. So this is a good problem statement to start with. It is called as the Titanic machine learning from disaster dataset. Okay, this Titanic dataset is one of the open problems that we see in Kaggle. Okay, so Kaggle is one of the platforms which we use for getting our data, practicing on multiple competitions, discussing on forums with other data scientists, and even learning a lot of material. Okay, so from the Kaggle environment, from the Kaggle's data set, the first data set that they promote for beginners to start with is the Titanic, and hence I take this Titanic for multiple reasons. This is a good data set, fairly advanced and fairly beginner level both. Okay, so it stands somewhere in the middle where we can learn a lot of things. Let me first explain to you what the problem statement is, and then we'll see what we actually will be doing within our pre-processing steps. Okay. So, okay, I just get the data. So I have a folder called as input, which has two files, test.csv and train.csv. I import pandas as PD and read both the CSV files, the train CSV into a data frame called as train, the test CSV into a data frame called as test. Okay, and if we explore, if we see what the data looks like, that is, if I do a head train.head, then I can see the first 5 columns of my training data. Okay, and as you can see, the first columns, okay, as you can see the first few columns, I have column names like passenger ID, survived, P class, name, sex, age, SIBSP, that is sibling spouse, PARCH, which stands for parent children, ticket, fare, cabin, and embarked. Okay, so these are the different columns from my data. Okay, the task here is to train a machine learning algorithm that can take this data and predict the answer, predict this column called as survived. Okay, so this is our target class. This is the target class that we are trying to find out. We are trying to predict using all of these different features that we have. Okay, like passenger class, name, age, sex, sibling, spouse, parent, children, ticket, fare, cabin, and embarked. We're saying if I have this information regarding a person, can I know if that person survived or not? So we must all be aware of the Titanic disaster that had happened years ago, where there was a huge ship called as Titanic, uh, which crashed or which collided with an iceberg, broke into two, and the 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 big ship was let me see, it was the big ship drowned. Okay, so that was the problem. Okay, just one second. Is there any way to load data without download? Because sometimes data amount will be large. So this is a different question. Okay, load the data without download. So I assume when you say load the data, you want the data to be into your RAM. And when you say you want the data to be into your RAM, you need to download it. Okay, that download can happen in parts, or that download can happen as an entire big package, depending upon your case. I would say if your data is too large that your RAM cannot handle, it would be smart to move to a cloud-based solution where you don't have limitations based on your individual PC that you are handling. Okay, if you're working on the cloud, you have a much bigger space that you can work with. Few of such examples are you can work on Kaggle's notebook, you can work on Google's notebook like collaboratory notebook, or if your company has a dedicated cloud solution, you can do it on that. Okay. I hope that helps. Anyways, so we are using all the other features this to try to predict the value of this survived or not. Okay. Now, many of these features may already make sense. Let me explain the ones that don't. So when we say P class stands for passenger class, which is the kind of ticket that the user or the passenger had taken. Okay, there are three types of tickets: class 1, class 2, class 3. Much like our trains, where we can take a local ticket, or we can take a first class ticket, second class ticket, third class ticket, and so on. Okay, depending upon that, we have a passenger class. Okay. Then name, sex, age is pretty self-explanatory. Let me tell you SIP SP, which stands for number of siblings or spouse aboard in the Titanic. Okay. So number of siblings or spouse aboard of the Titanic says that, so let's say here, when we look at this first passenger, Mr. Owen Harris, who is a male of 22 years, he was not traveling alone. In fact, he either had a spouse on the Titanic, or he either had a sibling on the Titanic. Okay, so either a brother or sister or a spouse on the Titanic. He was not traveling alone. That is what the sibling spouse means. Okay. Then we have another column called as PARCH, which stands for number of parents or children aboard the Titanic. Okay, so did they have any parents? Whoever the person is traveling, were there any parents on the Titanic, or did they have any children on the Titanic? Either of them holds true. So in this case, we see that no, Mr. Owen Harris did not have his parents or was not having children on the Titanic. Okay. Then we have ticket number is fine. This is the ticket number, fare is fine. Cabin is what cabin were they assigned to when they bought the ticket? Which cabin were they boarded in? Okay, so here we have a missing value for Mr. Owen Harris, but for Mrs. John Bradley, we knew that she was in the cabin C85. Okay. So that is what this column cabin means. Then we have an embarked column, and for that embarked column we have three values, either C, Q, or S. And what they stand for is from which place did these people board the Titanic from. So either from a place called as Cherbourg, or Queenstown, or Southampton, and so on. So there were three places that people boarded on the Titanic: C, Q, and S. So this is what our data is. Okay, and our task later on in the machine learning algorithm is for the test data. So this is the train data. Let me also show you some more things. If we do train.shape, we can see that there are 891 rows and 12 columns. If we do test.shape, there are 418 rows, 11 columns. Okay. So for the test data, I have just 11 columns. That is, one column is missing. What is that column? Survived. Okay. So I have to use all of this data to help to learn a model that can demonstrate or that can tell what are the people who have survived or not. Just one second. Okay. That will tell us which are the people who survived or not, and depending upon that, we can use and we can see if our model is doing good, bad, so on. So if I do something called as train.info, we can see some more information regarding our train data. Okay. So what do we see? We see that there are 891 rows or entries. They are labeled from 0 to 890. Okay, we have 891 rows, which their index goes from 0 to 890. We have several columns. We have 12 columns from 0 to 11. These are the column names. For each column, we can see the non-null count. That is, how many values are present. So we can see most of these values are 891. We have age, which has missing values. We have cabin, which has missing values, and we have embarked, which has a few missing values. Okay, so we get some idea of that. Then we see data types. So we can also see that passenger survived, P class, and sibling, spouse, parent, children are integer values. Then we've got object values for name, sex, ticket, cabin, and embark. And we've got float values for age and fare. Okay. So we also see that this data thus is not a very big data. It just takes 83.7 KB, or let's say somewhere around 85 KBs to load this data. Okay. If I look at the test data, we can see that now we have lesser number of columns, a lesser number of values. We have just 418 values, and these are the missing values. So again, we have some missing values in age. We have one missing value in fare, missing values in cabin and embarked as well. Sorry, in just cabin, not in embarked. And this data just takes 36 KBs to store. Okay. So from this phase now, actually, I'm doing multiple steps. Okay, we are doing exploration of the data, we are doing visualization of data, and both of these guys, exploration and visualization, will help us to do data preprocessing. Okay, so in this example, we are doing all of these three things. Okay, let me show you. So right now we are exploring the data to find out what are the columns, how are they arranged, and so on. So first, let us find out what are the number of missing values. So we can do that easily by doing train.isNull.sum. Okay, so that will train.isNull will convert all the rows and columns to Boolean numbers, that which has 1 wherever there is a missing value and 0 wherever we have a present value. And in this case, when we do a dot sum, what we do is we are adding all of those values together. So when we take Boolean values of true, which Python understands to be 1, and we sum it up, we get the total number of missing values. I'm additionally doing a sort values, that helps me to see this in sorted order. That is, which are the most number of missing values, then next, and so on. Okay. So this is for train. We can see 6 out of 891, 687 missing values, which is a huge number. That is more than 70 or 80% of data for cabin is missing. So we'll have to do something about it. Then we've got a few numbers missing for age and very few numbers missing for embark from the train dataset. Similarly, from the test dataset, we see that cabin out of 418, 312 are missing values. We've got 86 age missing values and 1 fare missing value. Now, since I said we will also be doing visualization, let me import Matplotlib and Seaborn so that we can get some plots. Okay. So that's what I've done here. Okay. Let me first show you a plot, then okay, all of this is something I was trying out. 1 second. Okay, so this is of my interest. I will I will go up and then explain what are the other parts. So first, I'm defining a function called as bar chart, and the purpose of this function is I can get a plot like this. Okay, so maybe first let us look at the plot, then we'll look at the code that helps us to get this function. So I'm defining a function called as bar chart, to which I will provide the feature. So in this case, for the function bar chart, I'm providing the feature called as sex, which has two different options, male and female. So sex is a categorical data. When I say categorical data, it means that I have a limited number of objects, limited number of values that feature can take. Generally, those number of values range from anything up to five or maybe even 10. Okay. Generally, more than that, we would say that they're not truly categorical. We could say that they're numerical in nature. Again, depends upon the size of data that we have. In this case, we have just two options, male and female, clearly showing that this is categorical data. And I'm creating a plot where I have two bars, okay, two stacked bars. One bar is called as survived, one bar is called as dead, which tells me how many people survived, how many people died, and along with how many people survived and died, it also gives me a division of how many of those people who survived were female, how many were male, and here how many of the people who died were female and how many were male. Okay, so maybe let me ask you a few questions. In this case, if you were a male, do you have more chances of surviving or dying on the Titanic disaster? Yes, males have a more chance of dying. We can see that by saying that in the dead category, in the dead column here, I have many examples of male. Okay, saying that, okay, if you were a male, more likely you did not survive. Okay. And if you're female, more likely you survived, because here the female category is more in survived compared to the dead. The male category is more in dead compared to the survived. Okay. On an average, for the data set we have, do we have more survivors or more people who died? Yes, your answer would remain same. It will be difficult to see because we can see from our plot here that around 340 or 350 people survived and around 550 or 540 people died. Okay, out of the 891 data points that we have, that is the division of the data. Now, to get this plot, we will look at what was the code written so that we can get this plot. So to get this plot, I'm creating a function called as bar chart, which just takes a feature inside. Okay, and inside I am then doing all of this stuff. So not too complicated. What I'm doing is first from the trained data set, I am choosing a subset of all the people who survived. Okay, so I'm saying from train, find all the rows in which the train survived is equal to 1. Okay, so that will give me all the rows in which people have survived. Then I go for the column here. Whatever column is passed as input, select only that column. So by doing this, I have a series in my hand. Okay, I have all the columns, all the data points for this feature for which the people have survived. Okay, then I do a value counts on it. So when I do a value counts on it, I will get the division of male or female, the number of males, at least for this feature, let's say when we say sex as a feature, we'll get the number of males and number of females who have survived. I do the same strategy for the next line, where now we are looking at just the people who died and then the division between number of males and females who have died. Once we have these two, I'm storing them into a variable called as survived and dead. I'm creating a new data frame, pd.dataframe, with the survived and dead features. And after doing that, I am also giving the index as survived and dead. After doing that, I'm creating a stacked bar plot that gives me this answer. Okay, so let me show you the individual steps that go along in doing these things. That is what all of this background is. Okay, so let me go here first. When I take train data set, and from the train data set, when I choose only the people who have survived for the feature sex, and I do a value count. So let me probably do it in bots. Okay. So if I just take train, I will have I will have the entire 891 rows and 12 columns. Okay. So that is that is the full sample space. Within that, I am now choosing to see only those columns for which people have survived. So just notice here, we have 891 rows, and out of that, you can see survived 0, 1, 0, 1, so on. There are many people who have survived, many people who have died. So when I do this subset and then now I execute this, I can see that I have shortlisted it to just 342 rows, and I have only the people who have survived. See all the people who have survived. Now this has all the 12 columns, but I'm not interested in all 12 columns. I'm interested is only in this one feature called as sex. So I will choose that feature, and when I execute, you see I end up with just a series object of size 342 with males and females. Now I want to know what is the distribution. How many males do we have? How many females do we have? And then we do value counts and execute. I can see that I have 233 females and 109 males. Okay, so this will be the data that will go into the function that helps to create that bar plot. Okay, so this is the data we're interested in. So we do this for survived. We do this for people who did not survive. We can see that distribution. Okay. Now these are okay. These are extra things that I'll remove these for now. Okay, this is for a different class that I was teaching, and then I had some questions. So I was trying to answer those using that. So I'll remove all of these guys. Okay. Okay. So I have not disabled annotation. Let me do that. Okay. Okay. So I have yes. So now we have taken the individual parts of this and joined them together. So we have the survived and dead. Let me show you what happens when we take that into a data frame. So let me put this into a variable called as survived, and this into a variable called as dead. Execute the code, and now create a variable df and do df here. Okay. So see, when I put this into uh, a data frame, I get this value. So I get a column called as female, which has the values 233 and 81. A column called as males, which is 109 and 468. But my index is not right. So the first index will be for people who have survived. Second index will be for people who have died. So either I can do this, or okay, I'll do this. Let me copy it, paste it here. Okay. Now I have the right index values as well. With this right index values, now I can do a plot. So when I do this plot here itself, you will end up with this plot. Okay, which is take df, make a bar plot. So do a plot with kind as bar, keep stacked as true, and figure size gives me the dimensions of this plot. Okay, so I put all of these things into a function so that we can use it again and again. Okay, I hope you have understood what this plot is. Let me maybe it would be a good exercise before going ahead to try to analyze this plot further and see how this plot can help us. Okay, so let's say if I have to predict, I have to take a model and I have to predict survived or died based on just this feature called as sex. Okay, just based on the feature sex, if I have to predict if someone survived or died, how would you create a model? What would your model look like? Can I have some answers on the chat? What would, based on this data, what would you say, what would you predict your model? Okay, or what would you say your model, how could you say you can use this data and say, now if I see someone as male or if I see someone as female, I will try to predict if they have survived or they have died. So let's say, maybe that's a difficult question to answer on chat. Let me ask you a simpler question. Okay, based on this data, if I tell you that I have a passenger who is a male, what would you say? Did he survive or died? Okay. And if I have a passenger who is female, what would you say? Survived or died? Okay, excellent. So basically, the way that you're defining the model is you have a binary model which says that which takes all females and puts and predicts for them as survived, and which takes all males and predicts for them as died. Okay, so I want to know what is the accuracy of this model. Okay, if I just create a model that divides based on males and females, what would be the accuracy of this model? Okay, so let me do some analysis for it. So if I say all females have survived and all males have died, I need to first look at my data and see what does the division look like. So if I do train dot group by, I'll say group the data by maybe uh, group the data by sex for survived and do a dot count. Okay, so okay, no, I have to group by this as well. So let me say group the data by survived and sex and just show me the count for survived. Okay, so here I have a grouped data which tells me that 0 means people who have not survived. Okay, so people who have not survived or people who have died, we have 81 females and 468 males, and for people who have survived, we have 233 females and 109 males. Okay, so for the simplistic model that we made, that is all males die and all females survive, can you tell me what will be the accuracy? Okay, what will be the accuracy of this model, or what will be the training accuracy of this model when we say that all females survive and all males died? Okay, so let me simplify uh, the question. So instead of asking accuracy, I will ask you individual questions. Okay, so when I look at the first row here and I say that 81 females have died, in this case, will our model be right or will our model be wrong? Our model which says all females have survived, for the first row, for these 81 data points, will our model predict right or will our model predict wrong? Excellent. Our model will predict wrong because we are saying that all females survive. For this case, for these 468 values, will our model be right or wrong? Oh, you guys are saying our model will be wrong? Okay, yes, I've got right. So maybe you can just put R or W so that you will have to chat less characters. Okay. So here we're saying people who have died, male 460 males who have died, which is right, right? Our model is saying only females survived. So in this case, when we say males died, our model is right for these 468 values. What about this 233 values? Is our model right or wrong? Right, excellent. What about this 109 values? Right or wrong? Okay, so we see that out of these 4 categories, we are right for this 468 and 233. That means our accuracy will be 468 plus 233 divided by the entire set. So entire set I know is 891. Okay, when I execute this, so our simplistic model, which says that all females have survived, all males have died, has a very nice accuracy of 78%. Okay, just by using one feature, our training accuracy is 78%. Okay, so you're saying not clear this. Okay, let me show you once again. Okay, so our model says that all females survive, all males die. Okay, then if you look at our actual data, in our actual data, for people who die, we have 81 females who die, 468 males who survive, 468 males who die. So our model here will be wrong on these 81 values, because we see that actually 81 female have died, where our model says that no, all females survive, all males died. So our model will be wrong for these 81 values. Our model will be right for these 468 values, where we say that males die. When we look at the next number, 233, these next 2 data points are for people who have survived. So 233 females have survived, which is right. Our model is saying all females survived. So this will be 233 right answers for us. And when we say that 109 males survive, our model will be wrong here, because our model says only females survive and males die. Okay. So in that sense, we have a sense of right and wrong. So our model will be right these 2 times, and our model will be wrong these 2 times. So our accuracy is the times we are right divided by the total number of times. So we are right in 468 plus 233 times, and we are wrong out of the total 891, which gives us an amazingly good result of 78% times. Our training, a simple model like this is even right 78% time. Okay, so we will stop here, and in the next class onwards, we will continue exploring the further part of our model. Okay. Okay, that's it. Thank you so much for joining. Let me stop sharing my screen. Nisha ma'am, I'll disconnect now. Okay.
Okay, sir. You can leave.
Okay.
Good morning, all of you.
Thank you so much.
Now, it's clear ga vastunda?
I cannot hear your voice. Can you hear me? Okay. I think my speaker was low. Thank you so much. See you. Bye-bye.
Okay. Good morning, all of you. మీకు ఎవ్రీ థర్స్డే యూ షుడ్ ఫిల్ ద 2 ఫీడ్బ్యాక్ ఫామ్స్. ఇక్కడ నేను షేర్ చేశాను, మీకు చాట్ బాక్స్లో ఫిల్ చేయండి. ఇంకొకటి ఏంటంటే, మీకు టెస్ట్ 2 వచ్చేసి మీకు అప్లోడ్ చేశాము ఈలర్న్ వెబ్సైట్లో. అది ఖచ్చితంగా అందరూ ఎగ్జామ్ రాయండి, మీకు ఒక ఐడియా వస్తుంది. ఓకే, ఎగ్జామ్ రాసిన వాళ్ళు వదిలేసేయండి, రాయని వాళ్ళు అయితే ఖచ్చితంగా రాసేయండి, మీకు ఒక ఐడియా వస్తుంది ఎంతవరకు మీకు నాలెడ్జ్ గెయిన్ చేశారు అనేసి. ఓకేనా, నేను టెలిగ్రామ్లో కూడా మీకు 2 ఫీడ్బ్యాక్ ఫామ్స్ షేర్ చేస్తాను, ఫిల్ చేయండి. ఓకే, థ్యాంక్ యూ అండి.